In this video, we're going to discuss the idea of a unit vector. This is a very particular type of vector, and it's going to be a very important type of vector, which is why it's getting its own video. The definition of a unit vector is very, very simple. So we're going to say that a vector v is a unit vector if the magnitude of v is equal to 1. All right, so this is where the unit part comes in. The magnitude is the length of that vector is exactly 1. Right? So we have in different in the R2 and R3 contexts, we have some very useful unit vectors that we're going to name. So in R2, we have a vector that we're going to call lowercase I, which is going to be the vector 1, 0. Okay. And we're going to have a vector j, which is going to be the vector 0, 1. Right? So both of these vectors obviously have magnitude 1. The magnitude of a vector it's just this square. You square each of the components, add them together, and take the square root. So when we square the components of either of these and add them, we get 1 squared plus 0 squared, which is 1, and we take the square root of 1 and get 1. So both of these are very easily shown to have magnitude 1. In R3, we have corresponding vectors. So we have vector I, which will have a first component of 1 and the other two components of 0. We have a vector j, which will have a second component 1, and the other other components will be 0. And then we have a third vector here that we call k, which will be the vector 0, 0, 1. Right? And likewise, all three of these are easily shown to be unit vectors. Notice that there is no k in R2. There's just no third component there. Okay? So these vectors show up really nicely in the graphical interpretation of vectors. So if we're looking at, say, R2, we'll start there, and I'll draw the first quadrant. The vector I is the vector 1, 0. So it will go 1 unit to the right and stop. The vector j is 0, 1, so it goes 0 horizontally, but it goes 1 unit up. So vector j will look something like that. Right, now, if you've taken linear algebra before, you know that these two vectors are really handy to do a lot of linear algebra with vectors in the plane, and we won't use anything from linear algebra, but there's a lot of overlap between this portion of the class and that course. But these vectors do play a major role there. In R3, it looks much the same way. And so I'll draw my three-dimensional coordinate plane. I have my vector I, which is 1, 0, 0, so it's going to go 1 unit in the x direction. So it would be something like that. J is 0, 1, 0, so it goes 1 unit in the y direction, which will be this. And k is 0, 0, 1, which will be 1 unit in the z direction, so it goes up 1. Right, so those three vectors look something like that. And just so we have a name for these vectors I, j, and k, we're going to steal this from linear algebra. We're going to call these the standard basis vectors. Right. So when we're talking about the standard basis vectors, we're referring to the vectors I, j, and k. You don't need to understand what a basis is for anything that we're going to do. It is a linear algebra term, but these sets of vectors do form a basis in that context. One nice property of the standard basis vectors is that every vector v can be written as a linear combination of those standard basis vectors. So what this means is that we can find any vector by multiplying each of the standard basis vectors by some scalar and then adding them together. And it's actually pretty easy to see how to do this. So let's say I had a vector v which was 3, 2, and -5. Well, anytime we have a vector in R3 like this, we can break it down as the sum of 3 vectors, where in each case, all of the components are 0 except for 1. So in this case, I can write this as the sum of the vectors 3, 0, 0, plus 0, 2, 0, plus 0, 0, -5. So I can break this vector up into 3 pieces, where each piece has only one non-zero component. Right. Well, then I can use scalar multiplication to write this as a scalar times a vector with just zeros and ones. So for example, I could have the first vector as 3 times the vector 1, 0, 0. This plus 2 times the vector 0, 1, 0. Minus 5 times the vector 0, 0, 1. Right. And of course, these 3 vectors that I've written out are the standard basis vectors in R3. They're I, j, and k, respectively. So this is just the expression 3i plus 2j minus 5k. Right? So this vector v that I picked, you can write it as 3i plus 2j minus 5k. And notice that this could go the other direction as well. If I had 3i plus 2j minus 5k, I could go right back up through this slide and find the component form of this vector as well. Right? So these are just 2 different ways that we can write vectors. And notice that the same numbers are used. It's just a question of whether we want to just include the coefficients in the appropriate order. And remember that the first is the x component, the second is the y, and the third is the z. Or if we want to use the ijk notation. And we will typically use both. Some contexts prefer the ijk notation, some prefer component form. So we will use both throughout the course. So it's worth being comfortable with going back and forth between them. But as you can see from this example here, it's very simple. It's the same 3 numbers. It's just how we notate those numbers. So now going back to finding unit vectors, let's look at the following example. So let's say we had a vector v. We could say 3, -2, 4. That's the component form. Or if we like, we can write it with the standard basis vectors 3i minus 2j plus 4k. Right, so these are the same vector, just written in the 2 different forms. So what I'd like to do, I'd like to find unit vectors in the same direction as v and in the opposite direction as v. And once we find one of these, the other is not terribly difficult to do. Right? So the first thing is we need to figure out the magnitude of v in order to scale it appropriately to make it have a length of 1. So the first thing is we need to find that magnitude or that length of v. Right? So to find the magnitude of a vector, we just square all of the components and we add them together and then take a square root. And so in this case, this would be the square root of 9 plus 4 plus 16, which is the square root of 29. Okay. So if this vector has a length of square root of 29, then a unit vector that we could pick, we'll call that u. What we could do is we could scale this vector by 1 over the square root of 29. Right? Remember that scaling a vector by a positive real number changes the magnitude by a factor of the scalar. So if we multiplied by 2, it would double. If we multiplied by 1/2, it would take half the magnitude. So if this magnitude is square root of 29 and we multiply by 1 over the square root of 29, this multiplies the magnitude of the vector by 1 over square root 29, and 1 over square root of 29 times the square root of 29 is 1. So this will always be a way to find a unit vector, is to take the vector and scale it by 1 over its magnitude. Right, and so in this case, we have v being 3, negative 2, 4. So we could write it as 3 over square root 29, negative 2 over the square root of 29, and 4 over the square root of 29. Okay. So this is a unit vector which is in the same direction as vector v. All right, it's in the same direction as v because this constant that we multiplied v by was positive. We did not change the direction. Right? So this is the one that's in the same direction. Now, if we want one in the opposite direction, then we could start with this particular vector. We now know this is a unit vector in the same direction, and what we really need to do is just make this vector turn completely around and point in the opposite direction. And so to find a vector that goes in the opposite direction of this, we multiply by the scalar negative 1. And so when we do that, we're just going to change the sign of all of the components. So this will be negative 3 over square root 29, positive 2 over square root 29, and negative 4 over square root 29. And so this will be the unit vector in the opposite direction. As an added bonus for an example like this, what we've done also allows us to write our vector our vector v that we started with in a really nice, useful form. Right. So, for example, I can take v. I'm going to leave a space here for now, but I'm going to write down the unit vector that we just came up with that is in the same direction as v. So that was 3 over square root 29, negative 2 over square root 29, and 4 over square root 29. Right? Now we know v is not equal to this vector because v had a magnitude of 29, and this unit vector, of course, has a magnitude of 1. And so one way we can get v from the unit vector is by multiplying the unit vector by the appropriate magnitude, which in this case would be the square root of 29. So if I have this unit vector, it has length 1. If I multiply it by the square root of 29, because that is a positive number, it'll stay pointing in the same direction, but the length will differ by a factor of square root of 29, which is exactly the vector v that we started with. And so what this allows us to do is, if we look at this vector in this particular form, right, we can see its magnitude. That's the number sitting out front. And we also have a direction given by a unit vector. Right? And going back to the definition of a vector, this is exactly what a vector is. It is a magnitude with a direction. And so this particular form is just one nice way of always being able to distinguish the two without actually having to do any other work. Of course, any vector form that we come up with, we could easily compute the magnitude. But in this one, it's staring at us right in the face, as is the direction. And so typically this is one way we'll think of that we'll use unit vectors, is that we'll use them to indicate the direction of various things. And so every vector, not just this particular vector v, but every vector can be written in this form by finding a unit vector in the same direction and then writing the vector as the magnitude times its directional unit vector.